that was close. Parking sensors save Americans thousands of dollars a year on average, and they also reduce backup crashes by almost half according to some sources. And this is actually all thanks to just a few vibrating rocks in your parking sensors. Now this happens because of the crystal's piezoelectric properties, which means that when mechanically deformed, it can create an electrical field, and then when exposed to an electrical field, it mechanically deforms. And this is useful for generating electricity, powering wristwatches, ignition buttons and gas burners, and even in creating sensors. Here's a model that represents what happens at the molecular level in the quartz crystal. These white parts represent areas of negative charge, while these black parts represent areas of positive charge. These trigons in the middle here, the white and black ones, represent the center of charge for each of the respective colors, with white again being negative and black being positive. And these areas of charge alternate between each other in a hexagonal shape as shown here. Now, let's assume you compress this structure from the top and the bottom. So you just push on the negative and positive ends, and as you can tell, the centers of charge are no longer aligned with each other, which creates a dipole moment. Now let's assume you expose the crystal to an electrical field. Let's say that you have a positive charge on the top and a negative charge on the bottom. You would expect the crystal to move towards those charges as such. This would create another dipole moment. Now let's say you were to flip the current so that you have a negative charge on the top and a positive charge on the bottom. You would expect the crystal to be compressed as such, which creates another dipole moment. Now this behavior is especially useful in watchmaking for quartz movements, where if you flip the current every few seconds, the crystal will vibrate as such.
In addition to quartz crystals, there are other materials that also exhibit piezoelectric properties, such as perovskite. Perovskite crystals are used in radiation detection as well as solar cells and photovoltaics. In addition to perovskite crystals, we have PVDF, or polyvinylidene fluoride. This is used in nanogenerators as well as robot tactile sensors. Japan uses piezoelectric floor tiles to convert footsteps into electricity. When people walk on the tiles, pressure creates mechanical stress that the piezoelectric material converts into electrical energy. Although each step generates only a small charge, millions of daily footsteps in busy areas like train stations can produce enough electricity to power LED lights, displays, and sensors. The energy can be used immediately or can be stored, making it a practical source of renewable energy. Car parking sensors use a lead zirconate titanate (PZT) crystal to generate and detect ultrasonic sound waves. The crystal vibrates at 40 to 48 kilohertz, sending waves that reflect off nearby objects. When the echo returns, it can cause the crystal to vibrate and produce an electrical signal. The car's computer uses this signal to calculate distance, increasing the beeping rate as the vehicle gets closer to an object.
From making sure you don't crash your car to powering the lights of one of the biggest cities on the planet, piezoelectric crystals such as this one and other piezoelectric materials have contributed to numerous technologies and are still contributing to many technological advancements. And this is all because of their amazing property to be able to generate electrical currents when mechanically compressed and mechanically expanded. And so next time when you're about to back up with your car, make sure to thank these vibrating crystals for potentially saving you on thousands of dollars worth of damage.